Hello. Today we will discuss regression problem here. We will approximate a linear function. We will approximate multiple variables linear function. We will approximate sinus function. And sphere surface we will too approximate today. Let's start. At first we need to install required libraries. Plotly for visualization, Torch for our learning process, and TQDM for visualization too. Okay. It's not really quickly process, but okay, it is done. Import libraries. Torch for our learning process, NumPy for calculating metrics, tensors, etc. Plotly for visualization, random it will be used for us for creating dataset, and PQDM. Okay, libraries are imported. Let's look at linear function approximation. Okay, here we want to approximate function that is depicted here, 3x plus 8. Okay, it is our target function. For learning process, we need a dataset. We need to generate the number of points that will explain our model how to predict this linear function. Okay, we will create function getDataSample that will create input information, our x respectively, and target output information. Yes, and it will return tuple of two values: input information and target. Nice. Let's visualize our data. Okay, you can see here a linear function that is described by the formula, by the equation, this equation. Y is equal to this. Okay, let's do this approximation with using neural network model that consists of only one phi-c layer. We will use here default class NN model. It is contained in Torch library, in Torch PyTorch framework, and it represents the simple neural network class. We will inherit our neural networks classes from this one. Here we can see two important methods in it, where the layers are shown that will be used in this model, and method forward that will describe an architecture of our neural network. Okay, here we have one phi-c layer. Phi-c layers are described by method linear in Torch framework, and these two numbers are, the first number is equal to the number of input neurons, input arguments, and the second one describe the number of outputs of this layer. Okay, here the number of input neurons is 1 and number of output neurons is 1, 2. Here we can see how this neural network looks like. Okay, nice. And in the end of our forward propagation that is described here, we return the result. The result is x. Let's look how it works. We need to define this class, and then, only then, we need to create an object of this class. We can print our network, our net, and it will show us information about architecture of this neural network. We can see that it consists of one fully connected layer, and input features is equal to 1, output features equal to 1, and bias, our input parameter that doesn't depend on input information. Okay, we can see the num of params here. The first one, weight, and the second one, bias. Okay, nice. Let's select the loss function for our model, learning rate for our model, and optimizer for our model. We will use mean squared error loss here, learning rate equal to 0.01, and optimizer equal to stochastic gradient descent with learning rate that is defined here, and net parameters that are defined here. This one. Okay, nice. I want to recall how does it work. There are different types of loss functions, and the choice of loss function depends on the task. So the first one, mean squared error, the second one, mean average error, and the third one, cross entropy loss. So here we can see models predictions, and correct answers. Our task is to approximate the linear function with coefficient 3 and the second coefficient 8. Okay, we want to approximate the linear function that looks like y equal to 3x plus 8. And we will do it with knowledge only of data, only of 3, for example, points of this linear function. Okay, for example, our data will consist of 3 points, 1 and 11, respectively, 2 and 14, and the last one, for example, will be 3 and 17. So, and what we have at the beginning? We have this data and our network, which is equal to this one. For example, x and y. 2 neurons, input and output. So, of course, here we have 2 parameters, weight and bias. And how we can represent it in mathematician way? It will be looks like this. Y equal to weight x plus bias. And what we want to do, we want to the model to get the weight value of 3 and bias predict the value of 8. And at the beginning, these values are different. They may be random numbers, and after learning process, we want them to get values 3 and 8 respectively. Okay, how we can do it? In the first step, we need to calculate loss function. We are doing forward propagation for calculating the model's prediction, and then we compare it with correct answers. For example, let's our start point of weight, weight sub 0, for example, will be 1, and bias will be, for example, 0. Let's calculate model's prediction. Okay. With input information equal to 1, respectively. Okay. 1 multiplied by 1 plus 0. And the prediction will equal to 1. Let's calculate loss function with using mean squared error. Our batch size is 1 because we want to calculate loss for only 1 point, for only one prediction. That's why this sum will consist of one element. Let's look. Model prediction 1 minus correct answers. Correct answers is 11. And our loss function will be equal to 100. Really huge number, really huge loss. And now let's calculate loss function using mean average error. Here we'll have an absolute sum. 1 minus 11 divided by 1. It will be 10. Okay, you see that mean squared error is more big than MIA, is bigger, and it will lead to different results of changing the weight value in further way. So after calculating loss, we need to define the step, to determine the step of our weight. How we can do it? We need to calculate derivative of this, yes, okay, and multiply it by learning rate, parameter that determines the weight step. This way we can define the change of our weights through one step of our learning process. Okay, after doing this, we can change our weights from weight sub 0 to weight sub 1, for example, where these numbers define the number of iteration of our learning process. Okay, and here we described the learning process for our network that is used for predicting this linear function. And after a couple of these steps, our weights will be equal to 3 respectively, and bias will be equal to 8 respectively. We select our loss function, learning rate, and optimizer. Then let's look at train loop. We will do 100 iterations. It means that we will change our weight, our values of weight 100 times. Okay, in the beginning we need to take our data, then we need to zero our gradients because our batch size is equal to 1, so we want to change our weights every iteration of learning process. Okay, then we want to take predictions, outputs of our model, compare outputs and target, and then get our loss. So loss value will be get by loss.item because loss is a tensor here. Then we want to take a look at our parameters through the learning process, through each 30 iteration number. So then we want to do back propagation and then change the values of our weight. And then look at how our parameter changed. Okay, let's look at how it worked. I'm so sorry. We need to select these entities at first. Okay. Our neural network is already learned, so we can see that at the beginning of the learning process, our weight and bias were equal to these values. And the loss value at first was equal to 70. But after, for example, 30 iterations, the values of tensors has been changed and current loss decreased. It's what we want, to decrease our loss through the learning. And at the end of the learning, here we can see that our weight and bias is really close to the ideal values, to 3 and 8 respectively. So here is 2 and here is 6. Okay, nice. Let's look at the end of the training process. Here, current loss is really small, less than 1, and weight and bias is close to real values. Okay, let's do the testing process on another data, on the data that didn't use in our training process. Let's look. So loss is really small and we like it. But now I want to say that we select the values for training from the small range numbers, from 0 to 1. In this range of numbers, loss is really small. But if we will look at big values, for example, x equal to 100 and bigger, we will see that our loss is not really small. Here loss is really big, it is equal near 600, but there is a reason for it. So let's calculate our derivative. Yes, let's look how this derivative is calculated. We have loss. Here we using MSA loss. Yes, here. That's why our loss is equal to correct answer minus weight x minus bias. And it means that after taking a derivative in power equal to 2, it means that after taking a derivative in weight, we will get this equation. 2 multiplied by this one and multiplied by x. So this means that our change of values of weights depends on x. That's why the bigger is the x, the bigger is the change of our loss function. Let's look at the results of our learning process. Okay, in the range of numbers from 0 to 1 to 2, the model predicts this line, this linear function, and it is cool. But if we look at far numbers, far values, it's not really good there. Okay, and now I want to present you a multiple variables linear function approximation. Here our target function will be equal to tensor, like this. We will generate in data as we did in the previous model. And this new neural network will consist of 3 input neurons and 2 output neurons. Okay, nice. You can see init and forward function because they are important here. Let's look at our new neural network. You see, one fully connected layer with input features equal to 3 and output features equal to 2, and bias is true. So here you can see the parameters of our neural network. Well, we will use MSE loss as a loss function here too, and we will use SGD here. but SGD with momentum. It allows us to recall the values of loss from last couple of steps. Okay, let's make a train loop. Okay, here we generate data, then make zero grad, get nets output, nets predictions, get loss, do back propagation, and then change the values of our weights. So at the first iteration of training process, here we can see the values of our weights and biases. And at the end of training process, it is really become closer to our real function that we want to approximate here. Okay, then let's look at test. Loss is really big. Let's make iteration steps bigger. And look at loss. Okay. Let's take a look at how our model predicts the points that are 100 bigger than in the dataset. And the loss is bigger too. So the reason of it is equal to the reason of the last model. We have already talked about it. Okay, and now I want to approximate a scene function. Let's do it. So we need to generate our data. Okay, let's look at it. Yes, nice. And now we will use a neural network that consists of two fully connected layers. And the hidden layer will consist of 5 neurons. So why we do it? Because our function that we want to approximate is not a linear one, and we need activation function for approximating it. We use here activation function tanh. Yes, we have learned it in the second lecture with you. It allows to make neural network predictions unlinear too. Okay, let's define it. Okay, nice. And now I want to start train process here. So we will use MSYLOS, SGD optimizer, and we will use epochs here for avoiding overfitting. And after each epoch, we will shuffle our dataset. We will change the order of our data in the dataset. After this, we will calculate output, get loss, zero grad, backpropagation, and changing the values of our weights. So, and here we can look at how training progress is. For this visualization, we use TQDM library. Okay, it is done. Let's look at the result of this training process. Okay, nice. So, in this small area, our approximation is really good. And we can see that the training loss is really big in the beginning of training process and really small in the end of this. Let's look how our model works at bigger values of points. So, it's not good at x points equal to 10, for example, and there is a reason for it. So our dataset should be representative. It means that, for example, here we need to add to our dataset points that are far from the area that consists of the numbers from 0 to 1. And it allows us to make predictions more correctly. Okay. And then I want to approximate sphere surface. Here, what will we do? We will have two classes of points, points that are inside the sphere and points that are outside the sphere. We will solve the classification task. How will we do it? We need to generate data, generate points that will be inside and outside, and separate them. Inside point will be described by value equal to 1, and outside points will be equal to 0. Then we need to change the view of these points, of these values to tensor torch.tensor. And then we need to create a sphere approximation neural network class. So here we will use two fully connected layers, and the hidden layer will consist of 10 neurons, respectively. The first one will consist of 3 neurons because we will walk in a 3-dimensional space, because sphere is depicted in this dimension. And the output will be equal to 1 neuron because there is only 2 possible answers: 0 when the point is outside the sphere, and 1 when the point is inside the sphere, respectively. So we need a method forward for describing architecture of our model. There we will select an activation function relu, yes, and after a second fully connected layer, we will use sigmoid function as activation function. Here we can see 2 differences. We will use BC loss, that is like binary cross entropy loss. It is used for binary classification, respectively. And as optimizer, I select Adam. It allows us to change learning rate through the learning process. So we will have 1000 iterations here. Other parameters are equal, and other logic is equal to previous examples. Okay, nice. We can see that our loss is decreasing through the learning, and it is cool. Let's look at our results. How we will visualize these results. We need predictions of our model, and we need a lot of points. We will work with the grid of points. Yes, it is creating here, and then we will put these points into model and look at predictions. And if our predictions will be less than 1.5, our points will be, let's look here, will be outside, yes? Because 0 value describes outside points. And if the prediction is bigger than 1.5 or equal to 1.5, we will look at a black point at the graph. For visualization here, I used matplotlib. So let's look at the results. Okay, the problem of matplotlib is that I cannot change the view of this, only with these params. You can see here. Oh. Yes? Let's look. It looks like sphere. That's why I can tell you that our learning process works correctly, and our model really predicts the points that are inside the sphere with the radius of 1. It is all I wanted to say in this seminar. Thank you for your attention.